Hello. In the next 3 videos, we are going to be discussing important reactions of alkynes. In this particular video, we are going to discuss the catalytic hydrogenation of alkynes to alkenes. The distinguishing feature of an alkyne is this carbon-carbon triple bond. In this particular structure, R or R prime or both could be hydrogen atoms or some other alkyl group. Just below, we've written it showing it as Lewis dots, and we see that carbon and carbon there each have an octet, so we're able to satisfy the octet rule by forming a triple bond. We have 3 electron pairs between the 2 central carbon atoms. From VSEPR theory, since we see around this particular carbon atom we have 1 electron domain, 2 electron domains, similarly for this carbon, that about the carbon-carbon triple bond we have a 180-degree bond angle, which is the same as saying that this particular region of the molecule will be perfectly linear. If one or both of the R groups on our alkyne is hydrogen, we have a special type of alkyne which we refer to as a terminal. Terminal meaning the end. So we have the carbon-carbon triple bond at the end of the molecule, a terminal alkyne. We can recognize this type of alkyne experimentally by reaction. So we react this with either silver plus 1 ion or with copper plus 1 ion, the so-called cuprous ion. In those particular cases, we get a structure like this. We'll show for the case of silver. We get a silver acetylide, and the key feature of why we could recognize this experimentally is that this is a solid that precipitates from solution. So we have a convenient way of experimentally recognizing terminal alkynes, and it's this reaction with silver plus 1 ion or copper plus 1 ion, the cuprous ion. The simplest and most important of the alkynes is this particular compound, which is called acetylene. For the specific case of acetylene, we're going to look at some of the general features of all the alkynes. So from the point of view of this particular carbon atom, it is attached to the hydrogen to the left and to the carbon to the right. So it's going to take at least 1 bond here and 1 bond there to hold the atoms together. The particular bond that's involved is a hybrid of the 2s and 2p orbitals on this carbon. So by combining the 2s and one of the 2p's, we make a bond that goes to the left and to the right, and that holds together carbon with a hydrogen and makes one of the 3 carbon-carbon bonds. So one of those is simply a sigma bond between an sp hybrid on this carbon and an sp hybrid on that carbon. This is similar to how in an alkene, the 2 carbons are held together by an sp2 hybrid. So we know that one of the carbon-carbon bonds is a sigma bond. What about the other 2 bonds? Well, just as in the case of an alkene, we know that we have p orbitals that are available on the on the carbon atoms. So just as in the case of an alkene, we have one set that is completely parallel to each other. So let's assume that it's actually going in this direction. So in the plane of the whiteboard, we have 2 parallel p orbitals on the carbons. So they overlap in such a way as to pi bond. If this were an alkene, recall that this is the reason why we have a buildup of electron density above the plane and below the plane, because of this overlap of p orbitals in the alkene. So this is the second of the bonds of the carbon-carbon triple bond. But we also have a third unavailable p orbital on each carbon, which I'll attempt to draw this way as a kind of fake three-dimensional. So this is supposed to be representing a bond that's essentially going into the plane of the board and perpendicular out. So I'm trying to draw a three-dimensional effect here, but such that this p orbital and that p orbital are orthogonal to each other. They're perpendicular. So similarly, we have a similar situation on this carbon atom. So even though it may be difficult to see, I'm trying to represent a situation where this 2p and this 2p orbital are parallel to each other. This 2p and this 2p are also parallel to each other, so they are available for pi bonding. The first of the three bonds here is a sigma. The second is a pi bond, as we have it in alkene. And now we see that the third bond of the carbon-carbon triple bond in an alkyne is also a pi bond. So we have sigma, pi, pi. Now, one thing which is somewhat deceptive about the way we've drawn it here, in addition to the fact that we're putting the p orbitals such that one of the carbon p orbitals is like this, and then the second is going in this direction, effectively because of the structure of the molecule, we get, rather than just above below the plane of the molecule and in front and back, effectively we get a cylinder of charge. So in an alkene, the buildup of electron density is above and below the plane, but in alkyne it goes completely and wraps around the carbon-carbon triple bond. So we get a cylinder of charge. As we'd expect by comparison with alkenes, because of this buildup of electric charge, alkynes, just like alkenes, like to react with electrophiles. So this video and the next two videos will discuss, among other things, the tendency for electrophilic attack on alkynes. Recall that for an alkene, we can catalyze the reaction of the alkene with hydrogen by using a catalyst. And the most commonly used catalysts are all in the same family of the periodic table. We have nickel, platinum, and palladium. And we can use nickel, platinum, or palladium to catalyze the hydrogenation of alkynes. Unfortunately, if we use those, we will take the alkyne to an alkene and then immediately onto an alkane. So if we don't want to do that, our ultimate objective is not to reduce the alkyne all the way to an alkane, and we want to stop at the alkene stage, we have two particular ways to do that. First, if we want to add the hydrogen atoms to the same side of the alkyne, so this is what we call syn addition. And this is typical for reaction with nickel, platinum, and palladium, for example, in alkenes. So this is so-called syn addition, and it's syn addition because the two hydrogens are added to the same side of the alkyne, resulting in a cis-alkene. So if we want to do this, the catalyst that we want to use is called the Lindlar catalyst. And the Lindlar catalyst is specially prepared palladium on calcium carbonate. And there's some additional things added to it, but most importantly, it's the specially prepared palladium on calcium carbonate with some other additional minor ingredients. And the key feature of the Lindlar catalyst is not only that it catalyzes hydrogenation of the alkyne by syn addition, it stops at that stage. So it stops at the alkene stage. with the Lindlar catalyst. Now suppose that again we hydrogenate our alkyne, and the rate limiting step in every case will be the breaking of the hydrogen-hydrogen bond into hydrogen atoms, which are hydrogen-free radicals, which are electrophilic and attack the electron-rich cylinder charge around the carbon-carbon triple bond. But suppose what we want to do is have the hydrogen atoms add to opposite sides of the carbon-carbon triple bond, which then becomes a carbon-carbon double bond. So recall that when we have an alkene, we have a carbon-carbon double bond, we don't have free rotation around this bond. So if the hydrogens are on opposite sides, we have the trans isomer that will stay like that. It won't interconvert to some other isomer. So if we add the hydrogens this way, we have so-called anti-addition. Anti for its being on the opposite sides of the carbon-carbon double bond, rather than on the same side, which would be syn addition. So, do we actually have a way of catalyzing the reduction of an alkyne to an alkene, and in the process getting anti-addition? And we do. And the key way to do that is to dissolve either lithium metal or sodium. And we dissolve them in liquid ammonia. So in this particular environment, where we've dissolved one of the very active metals, lithium or sodium, in liquid ammonia, we can not only achieve anti-hydrogenation of an alkyne, it will stop at the alkene stage. So it will not continue on to form an alkane. If you want to form an alkane, we can use the old strategy of simply using nickel, platinum, and palladium as a heterogeneous catalyst, and we can add enough hydrogen and we'll be able to reduce the alkyne all the way to an alkane. But if we want to stop at the alkene stage, and we want, as a result, the trans isomer by anti-addition, we can do it by putting either lithium or sodium in liquid ammonia and reacting it with our alkyne to get the desired alkene. Now we want to look at some specific transformations of specific alkynes. As we had mentioned previously, the simplest yet most important of all the alkynes is this particular compound, which we call acetylene. It also goes by the IUPAC name of ethyne. A small warning, particularly to students. Even though the textbooks always list ethyne as the IUPAC or official name for this compound, it is virtually never referred to as ethyne. In almost every single case, in research and in real life, we call this compound acetylene. Anyway, so if we react this with hydrogen gas, we are able to reduce the alkyne to an alkene, and again we have an incredibly important alkene, which is called ethylene. Ethylene is widely used industrially as a gas to accelerate the ripening of unripe fruit. So it is the only gas that is also a plant hormone. Now, because of the way, starting with a structure where we have hydrogens at both ends, whether we add hydrogens to the same side by syn addition, or we add to opposite sides by anti-addition, we get exactly the same resulting compound. So for acetylene, if we want to hydrogenate it and stop it at the alkene stage, we can use either the Lindlar catalyst or lithium sodium in liquid ammonia to get exactly the same product. Now please see several figures showing the computed structures of acetylene and ethylene in the gas phase. The next most complicated alkyne has the following structure. So we do have a carbon-carbon triple bond, but also a carbon-carbon single bond. And this compound is called propyne. If we would like to catalytically hydrogenate this, so we react it with H2 gas, in the presence of the proper catalyst, what do we get? Well, we know that we reduce the carbon-carbon triple bond to a double bond. And we have on this side, we have a methyl group. And the resulting compound is called propylene, is its common name. But it also is known in the IUPAC form as propyne. Another thing to notice, a couple things to notice here. Propyne has attached directly to the carbon-carbon triple bond, it has one hydrogen atom. So this is a terminal alkyne, just like acetylene is. So we can detect this experimentally by reaction with silver plus 1 or copper plus 1, the cuprous ion. Depending upon which catalyst we use, we get exactly the same resulting structure of propylene, propyne here. So it does not matter whether we have syn addition or anti-addition again. So we can use either the Lindlar catalyst or lithium or sodium metal in liquid ammonia and get exactly the same alkene. If we simply use nickel, platinum, and palladium, or palladium, as our catalyst, we would reduce the propyne all the way down to the alkane, which would be propane in that case. Please see the following figures which show computed structures of propyne and propyne in the gas phase. The next alkyne that we want to look at has this particular structure. So we notice that it has 1, 2, 3, 4 carbons. So we name it as a 4-carbon derivative, and we recall that BUT, as in butyl or butene, is the root that we use for 4-carbon chains. We also want to acknowledge the fact that it has a carbon-carbon triple bond, so that tells us that we have a butyne. But we notice that we could have, in a 4-carbon chain, we could have the carbon-carbon triple bond between the first and second carbons, or between the second and third carbons. Again, we use the principle that we want to keep the numbers as small as possible. In this particular case, this is between the first and second carbon, so this is 1 butyne. We also recognize that we have a hydrogen atom directly connected to the carbon-carbon triple bond, so we would conclude that 1 butyne is a terminal alkyne. So now let's suppose that we want to reduce this by catalytic hydrogenation to an alkene. So again, we're going to react with hydrogen in the gas phase. And what will we get? So what we end up getting is, just show the carbon part of the structure here. We get the following structure. I've omitted the hydrogens here just for the sake of completeness, but we have the bonding correctly in place. So the resulting structure here is a compound which you recognize as 1 butene. So we notice at the carbon-carbon double bond, because there's 3 hydrogens of the other groups, there is no difference between a syn or an anti-addition in the case of 1-butene. So again, if we want to reduce from 1-butyne to 1-butene and stop there, not go all the way to butane, we use either the Lindlar catalyst or the lithium or sodium metal in liquid ammonia. So far we've noticed that for every case of the alkynes, it didn't make a difference which of the 2 specialized catalysts we used if you wanted to stop at the alkene, because there was no ultimate differentiation in the product. So first, please see the following figures to show computed structures of 1-butyne and 1-butene in the gas phase. And then we're going to see, after that, the first example where the specific catalyst used will make a difference in the product that we get. Here we have another 4-carbon chain containing 1 carbon-carbon triple bond, but now we see that the carbon-carbon triple bond is between the 2nd and 3rd carbon atoms rather than between the 1st and the 2nd. As a result, we call this compound 2-butyne. It is also sometimes called, considering it to be a substituted acetylene, called something like dimethyl-acetylene. So if you see dimethyl-acetylene, they're also referring to the compound that we are referring to here as 2-butyne. Notice also that it directly attached to the carbon-carbon triple bond, we have methyl groups, but we don't have a hydrogen atom. Therefore, 2-butyne is not a terminal alkyne. And if we react it with silver +1 or copper +1 ions, we will not get that resulting precipitate. So we'll be able to tell experimentally that 2-butyne is not a terminal alkyne. Again, the common theme in this video is that we're reacting with hydrogen gas to form an alkene, and we want to stop at the alkene stage if possible. So in this particular case, suppose first that we add hydrogens to the same side of the carbon-carbon triple bond. Well, what will we get? We know that when we add the hydrogens, it breaks one of the carbon-carbon bonds, so we go from a triple bond to a double bond. And we've added the hydrogens to the same side. So this is, as we recall, the syn addition. So here we have syn addition to the carbon-carbon triple bond. So what would we call this particular product? Well, we see we have 4 carbon atoms, so we know it has to be a but something, and since it has a carbon-carbon double bond, it must be a butene. And since it's between the 2nd and 3rd carbons, it must be 2-butene. But even more than that, we see that we have the methyl groups are on the same side of the carbon-carbon double bond. And we don't have free rotation around the carbon-carbon double bond, so once they're both on the same side, they're going to stay on the same side. Therefore, the complete name for this particular molecule is cis-2-butene. So if we want to achieve this particular transformation, we want to be sure to use the Lindlar catalyst, because the Lindlar catalyst will give us this syn addition, and as a result we'll get the specialized compound, the special isomer cis-2-butene. But suppose we don't use the Lindlar catalyst. Suppose we decide to use lithium or sodium in liquid ammonia. What do we get then? Well, as we add to the carbon-carbon triple bond, its bond order is reduced down to a double bond, so we have carbon-carbon double bond. The catalyst adds hydrogens to the opposite sides of the carbon-carbon double bond, so-called anti-addition. And then we have the rest of the carbon atoms follow along, and we see a difference here. So this is the anti-addition, so we put anti down. And we only get this from the lithium or sodium in liquid ammonia. Now the methyl groups are on opposite sides of the carbon-carbon double bond. And now we have the isomer that is trans-2-butene. So we actually have the first example we've seen so far in this video where there's a difference, we actually see a difference in the resulting product by using a different catalyst. Just to remind you, if we had just decided to start with 2-butyne and used ordinary nickel, platinum, or palladium as our metal catalyst, we would have reduced 2-butyne all the way down to N-butane. So we would not have stopped at the alkene. But if we stop at the alkene, and we want to stop at the alkene, we use either the Lindlar catalyst or the active metal in ammonia, and depending upon which catalyst, we get a different product. So it shows that we're able to control exactly where the hydrogen atoms go in the hydrogenation of alkynes by use of the suitable catalyst. Suppose we have an alkyne with 5 carbons. So here we see we have 1, 2, 3, 4, 5, and we recall that the root that we use for 5 carbon chains is pent, P-E-N-T, and then we have to name it as an alkyne. So this is going to be a pentyne. We notice that with this many carbon atoms, we have a couple different locations where we might put the carbon-carbon triple bond. Since here is between the first and second carbons, this is 1 pentyne. Hopefully by this point the student is yelling at the screen saying, I also recognize something here. I noticed that we have a hydrogen atom directly connected to the carbon-carbon triple bond. So therefore we must have a terminal alkyne. So 1 pentyne is a terminal alkyne, and I know that I can prove this experimentally by reaction with silver +1 or copper +1 ion. So, can we catalytically hydrogenate 1 pentyne? Sure we can. So we can react it with hydrogen gas, and if we want to stop at the alkene stage, we know that we have the 2 catalysts that are available. So let's look at the possible products. Now because whenever we have these terminal alkynes, it works out that whether you have syn addition or anti-addition, you're still going to have hydrogen on each side. So we're not going to get anything isomerically interesting to occur in that case. We might get isomerization of the carbon chain down here, but we're interested in this case in isomerization around the carbon-carbon double bond, and we see that whether you if we flip this, switch this hydrogen with this alkyl chain, we still end up with exactly the same isomer. We just flip the compound over. So therefore, it doesn't matter which of the 2 catalysts we use if you want to stop at this stage, and we recognize that this is 1 pentyne. So we notice that whenever we have a terminal alkyne and we catalytically hydrogenate it, it doesn't matter which of the 2 catalysts we use, whether we use syn or anti-addition, as far as the resulting product is. So please look at the following figures to see the structures of one pentyne and one pentyne as computed in the gas phase. The penultimate molecule that we're going to investigate here is, again, we have 1, 2, 3, 4, 5 carbons. So we know it must be some pentyne, but now the carbon-carbon triple bond is between the second, so we have third, 2, 3, 4, 5, between the second and third carbon atoms. So this is now 2-pentyne. As a self-test, will 2-pentyne react with silver +1 or copper +1 ion to yield a precipitate? The answer is no, because we don't have a terminal alkyne. We don't have a hydrogen directly attached to the carbon-carbon triple bond. But now, let's catalytically hydrogenate 2-pentyne. So we want to react with hydrogen gas using a suitable catalyst to stop at the alkene stage. So let's just first put down our carbon-carbon triple bond. Once it reacts with hydrogen, this is going to transform into a carbon-carbon double bond. If we use the Lindlar catalyst, both of the hydrogens will be on the same side. So this time I'll write it with them on the top, but they're both on the same side. These two carbons are the carbons that are in the carbon-carbon triple bond here. So we know attached to this carbon, the other bond goes to a methyl group. And then attached to this carbon, we have an ethyl group here. So we have CH2, CH3. And we see, since we use the Lindlar catalyst, that we have syn addition. Make sure I write that down. We have syn addition. And therefore, our resulting product is now where we have the hydrocarbon groups are on the same side, or we can think that both the hydrogen atoms are on the same side. So now we have the cis conformation. This is both on the same side. So this is cis 2-pentyne. So we get the specific cis isomer by reaction using the catalyst that we pick, which is the Lindlar catalyst, to achieve syn addition. Please see the following figures to see what this looks like in the gas phase. Now, suppose instead of using the Lindlar catalyst, we had used lithium or sodium metal in liquid ammonia. Well, what would we get then? Well, we would have reduced our carbon-carbon triple bond to a double bond, but now with the hydrogen atoms on opposite sides. So let me just note this right away. This is anti-addition. Anti because it's on opposite sides of the carbon-carbon bond. And let's fill in the rest of the resulting product. So we have the methyl group here be above the carbon-carbon double bond, whereas the ethyl group is going to be on the other side. So now we have the 2-pentyne, but in the trans conformation. So by using, put this here, remind us that this is, we got this by using lithium or sodium, and this is going to be in liquid ammonia. We get, as our product, instead of the cis isomer, we get trans 2-pentyne. As a summary, please see the following table where we've listed the computed enthalpies of hydrogenation for each of the alkynes that we've discussed in this video. Also see as a comparison the related computed enthalpies of hydrogenation for alkenes. Now there was a video about that also, but you can see in the table how the enthalpies of hydrogenation for alkynes are systematically higher than the enthalpies of hydrogenation for alkenes, showing that the third of the pi bonds, the third bond which is a pi bond, is even more reactive than the second bond, the first pi bond that we have in alkenes. As always, I thank you very much for your attention. Have a good one.